Hello everyone. Today we'll start with week 3, session 1. And this session talks about Kubernetes fundamentals for AI workloads. Here we'll just recap as to where we left week 2, right? In week 2, we saw that there was one machine. We containerized the GPU workloads with Dockers. That basically meant the Docker had images. It had CUDA based images and we reproduce the builds. And we also showed that one GPU, there can be many jobs, and then how is that the CUDA visible devices show us which GPU we are working on. And then almost every technique we ran in the last lab had one host, and we actually also saw that for real training and serving needs, many hosts, many GPUs with many teams are working together. So now the question for this week is that how is that we would use a system wherein we are working with many nodes, many GPUs, many people, and all of that, how is that is being coordinated or orchestrated. For that reason, in week 2, we scheduled our work on a single Docker host and we scheduled it ourselves, right? But now we would see as to how a Kubernetes like software could actually schedule the job for us. So, this is what we are going to discuss in this week. We'll be doing hands on, and I have intentionally done it on the laptop so that you also could practice and then gradually shift that to the data center GPU when you have access to. Okay. So now the problem is that one node is not enough, right? From the capacity point of view, if you see a single training job might need 864 or 512 GPUs across many physical hosts. In the sense, you will not have that type of a setup in just only one box, right? And then when you want to share the resources, there would be multiple teams which would be competing for the same GPU resource, right? And someone or the system administrator has to enforce this fairness and prevent starvation among the team members, right? And we also want resilience, right? We would actually see that a lot of hosts are going to fail, the jobs will crash, and nodes will get drained because of the want of maintenance. And work must be rescheduled automatically, right? That is the intention. So even if one node fails, the work running on that node, okay, need to be actually shifted to another node which is working, right? So that is what basically is our intent of trying to understand how automatic scheduling of the jobs could be done very easily with certain specific softwares, right? And if we see how we actually would be doing this by hand ourselves manually, is that we would write something like this, right? SSH GPU node 7 Docker run with so many GPUs and so on and so forth. Okay, so we are basically trying to tell our system that manually our Dockers should run on node 7, which has a GPU and which basically will be using 4 GPUs, right? Okay, or what would happen if node 7 has just died? Now what? Okay, who is going to track which team is using this GPU, or how is that we are basically trying to support that team for some other GPU, because they would have put their workload, okay, to get executed on their GPU, and maybe it would have consumed maybe 20 hours of time and then it crashes. What's going to happen, right? This is exactly the gap which Kubernetes closes. So it's basically a control system that places watches and reschedules the work across a fleet. Okay, that is basically the intent of this particular week. Okay, so let us try to understand in brief as to what a container orchestration means, right? So in plain language, okay, we can define orchestration as a software that decides where our containers will run. They will be kept running, and reaction will automatically happen when the reality changes of the setup or the environment in which our containers are running, right? So the state change can be a node fail, or it can be load spike, or a job finishes, right? So these are the three conditions under which the state of my total container environment, so as to say, is going to change. So let us say we want, right, or I declare that I want three replicas of this container, each with one GPU. This is my requirement, right? And why do I want it is a different issue altogether. As we start programming, we'll try to understand that. But for the time being, let's assume that I want three replicas of a specific container, right? Each running on one GPU. Now, who is going to watch, right, it? So the orchestration mechanism is that orchestration software, okay, is watching it. It continuously compares the desired state to the actual cluster state. Okay, it reconciles, it starts, stops, or moves containers until reality matches our declaration. Okay, so we want certain specific thing. It is going to watch the state of the cluster at present, and then it is going to rearrange, right, all the things in such a manner that if possible, if possibility exists, right, so whatever we declare, okay, we will get that. That's what it means. Okay, so Kubernetes is one type of orchestration software basically. And Kubernetes is spelled as K8s, K3s. Okay, it's a lightweight version. K3s is a lightweight version, so we would be using K3s also sometimes. Okay, so K8s basically means we have 8 letters between K and S, so Kubernetes, right? So that's why that name. Okay, it's a standard way of naming certain specific softwares. Now it's an open source system for automating deployment, scaling, and management of containerized applications. So containerized application basically means we'll be working with Dockers, right? Now, how did it all start? It all originated because of Google's internal Borg system, which it open sourced in 2014. And it then donated to a vendor neutral community and so on and so forth. The current stable line is version 1.36, and we are going to use this release itself in our course, right? And why basically Kubernetes was very, very successful? We had actually a very good ecosystem, right? Which was there. So we had Helm, Argo, Kubeflow, Ray. Okay, all of these basically were either doing something which Kubernetes wanted to do, okay, or gradually they started supporting this type of orchestration, right? And basically we had a lot of broad cloud support since Google was involved, and an API extensible enough to model almost any workload including GPUs. So Kubernetes is just not for GPUs, it would actually do that for CPUs as well. So multi-core systems will have lot of multi-core CPUs or multi-core cores that also could be actually orchestrated, right? So but since we are working on AI workloads, we are concentrating more on GPUs. So I am going to show you GPU workloads. How do you access GPUs? How the pass through happens? Okay, and so on. So the basic idea is to understand how we can work with GPUs using Kubernetes, right? So now there are so many other things which we can work on with Kubernetes, or there are certain other softwares which basically can be equivalent to Kubernetes in certain conditions. So Docker Compose is one, Docker Swarm is one, Nomad is one, Kubernetes is the other one. So we are trying to understand certain alternatives as to why we will go in with Kubernetes, why not with others. You can work with others as well, but for the sake of working on for this particular course, we have chosen Kubernetes because when you work on the data center clusters, you would require basically this type of large cluster management requirement, right? And which can be supported by Kubernetes. So scope, if you see the Docker Compose, Docker Swarm, it starts with single host up till multi workload, and Kubernetes gives us access to larger clusters. Okay, so GPU scheduling in case of Docker Compose, we do manually. We saw it, right? Docker Compose, Docker Run in the initial labs. And Docker Swarm is a basic thing. Nomad uses a plugin based approach to GPU scheduling. Here we have got native plus DRA. We'll discuss what DRA means, but for the time being, let's assume that is the way of GPU scheduling. Ecosystem wise, largest ecosystem, right? As I told you, the Kubernetes one. And from the multi-tenancy point of view, okay, in Nomad we have namespaces. Docker Swarm also works on limited namespaces. Docker Compose does not have multi-tenancy type of a work, but here we will have RBAC plus quotas. In brief, we will discuss, and maybe in the next session we'll try to go into some advanced things of Kubernetes. Okay, sometimes labs, sometimes just theoretical based on the situation, but we'll try to cover that as well. So Compose and Nomads are great at smaller scope. K8s wins once you need multi-team, multi-GPU, self-healing infrastructure. So that's why we are going into Kubernetes. So let us try to understand why Kubernetes is a very, very important software for orchestration, or in the AI infrastructure per se. If you see Kubernetes, it's one of the important components, right? And why is it accounted for that? The basic idea is it can scale, right? We can orchestrate hundreds of GPU nodes, auto scale based on the queue depth. It can give us isolation between each team's namespace plus RBAC separation it gives. Okay, and it gives fair share GPU quota to all of the teams. And the reproducibility from that point of view, you can actually work with containerized workloads, same image from laptop to multi-node cluster. So that basically means once you containerize a workload, okay, the same image can be run on a laptop as well as on the multi-node cluster, right? So generally, the industry standard for ML platform teams is MLflow, Kubeflow, Ray, and Argo. And all of this, right, basically run on top of K8s. Okay, so these are all certain specific standard ML platforms which people use, okay, for various applications. I'm not going into the details of each one of them, but since I told you about the ecosystem per se, so these are used in parallel with Kubernetes sometimes, in conjunction with Kubernetes sometimes, but these are certain ML platforms which people use, right? So from K8 in 2026, 1.33 to 1.36, as I told you, ships with dynamic resource allocation, very, very important. So I told you about DRA, right? And it basically gives you about certain composability. And then there is this Carpenter version 1.3, which supports Blackwell B200 GPU shape provisioning. Okay, so I'm not going into Blackwell B200 GPU series, but basic idea is you should understand that Kubernetes supports Blackwell series as well. So okay, so now just a very very brief idea about Kubernetes architecture. Okay, very very brief. So we know that we have two things, right? One is the control plane and another one is the data plane. And control plane basically is something which is going to control everything, whereas data plane is supposed to be considered as worker nodes, right? So control plane controls the whole Kubernetes scheduling, right? Server access to API gateways and all of that control. Whereas data plane has got three things, right? Kubelet, kube proxy, and container runtime. So let's start in brief about what control plane components basically do. So we have this API server here. So it is a gateway for all control plane operations. Every kube control, webhook, and controller goes through it. So we are talking of the API server access, right? So for all operations, for all webhooks, right? All of that. So etcd is distributed key value pair store, source of truth for all cluster states. Okay, so this basically is a very very important thing of trying to understand the cluster state. Okay, so API gives us the control plane operations for all connectivities. This gives us the state of the cluster. Scheduler basically matches pods to the nodes based on resource request, affinity, and taint and toleration rules. We'll discuss about taint and toleration in next few slides. Even though we would be working sometimes when the error comes with taints, but at present maybe certain labs will not be working with taints basically, but in theoretical concept I will tell you what does that mean. Okay, but the basic idea here is that scheduler is going to match pods to the nodes based on the resource request, affinity, and certain rules. And from the worker nodes point of view or from the data plane, we told you that we will be having kubelet, kube proxy, and container runtime. So here node agent starts the container, reports the node status. So kubelet does that. Kube proxy gives us the networking options, right? For trying to connect everything. Okay, and then container runtime is container 2.0. Okay, and it pulls the images, runs the pods, so on and so forth, right? So this is the basic idea about Kubernetes architecture. We'll try to discuss what pods are and what nodes are as we go along, right? So try understanding that the control plane is basically something like this. You have a API server, okay, which does the authentication, validation, admission, and this is the only door in, okay, uh, to our Kubernetes cluster. Okay, so through the API server, we're going to access everything. Okay, etcd watches API server, okay, and persists the desired state. Scheduler watches for unscheduled pods, assigns the nodes. Controller manager runs reconciliation groups, deployment, etc. Okay, so the control loop basically in one sentence is that every controller repeats, observes the current state, compares to the desired state, takes the action to close the gap. So scheduler is just one controller. It watches for pods with no node assigned and picks one. So that basically means if there is a pod with no node assigned, it's going to basically assign a node for that pod. Okay, and the controller manager runs many such loops in parallel. It will talk about deployment, replica set, nodes, and more. Okay, so let us try to understand that there is a controller manager, there is a scheduler, and there is a watcher basically, right? Which watches the server as to who is entering, who is not entering. Okay, so something of that sort. So data plane basically we have this worker node which basically starts with kubelet. So kubelet polls the API server, starts stops the container, and it tells us about the health of the node. Okay, kube proxy at the same time uses IP table, okay, and routes to the pod's IP address, and it tries to connect, right, our programs with those live pod. Okay, and container is CRI compliant runtime, pulls the images, runs the actual container. So pods run here as one or more containers sharing a network namespace and optional volumes. So this basically means our pods are running as one or more containers. So our pods will be running, okay, uh, in this type of a environment with a network namespace being shared, okay, and certain volumes also shared in case we use those switches and then run our pods. Okay, so the GPU specific job, uh, why GPU specific? Because we are trying to work on AI workloads. So kubelet actually loads the NVIDIA device plugin, which advertises nvidia.com/GPU as a schedulable resource. Okay, so kubelets actually polls the API server, tries to understand, right, and it can also load the NVIDIA device plugin, and then it advertises GPU as a schedulable resource, and then this container hands off to the NVIDIA container runtime, uh, and it exposes the physical device inside the container. So this is where lot of errors will crop up when you try to execute it. So please understand that you're working in a containerized environment, okay, and then you are trying to work either on Windows or Ubuntu or any system with Dockers. So that containerized environment, and then the pods which you are creating, and then the pass through. Okay, so everything should be synced actually. Okay, and then you should be in a position to access the actual GPU hardware. Okay, so that is where a lot of issues will arise, and you can debug it. If not, then you can send me a message, okay, through the portal, and then we will see if any specific problems are there we can solve. So this is a very brief thing about how kube control is going to basically apply for a request. So kube control sends the pods manifest as an HTTPS request to the API server. API server will authenticate us, validate the YAML, runs the admission webhooks. The object is persisted to ECTD as the new desired state. Scheduler notices an unscheduled pod, picks the best fit node, writes that back. Kubelet on that node sees the assignment, pulls the image, and kubelet reports running status back. So this is the actual 6 stage which happens when you actually use cube control to apply for a request. Okay, and then the cube control actually reports that this particular thing gets the pod, and so on and so forth. But this will be clear when we try to run our programs, right? But this is just a theoretical thing about how those steps are actually run. Okay, so let us try to understand core Kubernetes objects. So pod is something which I was talking about, right? Pod. So pod is the smallest deployable unit in a Kubernetes. Okay, so one or more containers sharing the network and storage, and pod is something which runs our container. Okay, so we have a pod. It is the smallest deployable unit for mm, for the system. Okay, and then it is running our container. So what does deployment mean? When I say smallest deployable unit, it means pod is the minimal thing which can be deployed. Okay, and when I say deployment, it means so many pods are running. Okay, and Kubernetes is trying to schedule, watch, and maintain the state. Okay, so it manages a replica set. Declarative rollouts and rollbacks is what deployment means actually in terms of core Kubernetes object management, right? And service means we are talking of networking abstraction. There is a cluster IP, node port, load balancer, so on and so forth. So every service about networking and abstraction basically is considered under service. And config mac bar secret, these are credentials basically. So how do you actually decouple configuration from an image? How do you actually use certain base 64 encoded information for production, so on and so forth. And persistent volume claim is a storage request. So this basically means we can request for durable storage bound to a storage class, right? So these are certain things which talks about how much volume of storage we require for each uh, pod, and in turn basically how much our container could be in a position to access the volume. Okay, so these are certain things which we are talking about in terms of Kubernetes objects. So let us say, what does it mean when I say we are using a pod, right? Or a pod starts and stops together with the container, right? So pod basically is a shared network namespace plus volume. So let us say we have a container which has PyTorch, and it is a main process. It requests one GPU. Okay, and then there is this another container which is a log shipper, which is an optional thing, and it basically uses the shared local host uh, and volume with the main container. Okay, so the basic idea is there is this pod. This pod will have two containers running, and each of them can use the same local host, okay, for communication. Okay, so that basically means IP address wise, if you see one pod IP shared by every container inside it. So the basic idea here is there can be lot of containers running on a pod, and that pod basically will be a shared network namespace and volume, and it has got one IP address basically. Okay, and it will be shared by every container inside it. Storage basically means volumes mount into any container in the pod. So all the containers will be able to access that volume mount of storage. Okay, and life cycle basically means containers in a pod start and stop together. So the basic idea here is that all the containers in a specific pod will start together, coordinate among each other, and then if it is stopped, they all stop together, right? So this is the basic idea about how does a pod function, right? And what does pod anatomy mean? Okay, okay. So deployment, replica sets, and rollouts. So this basically means um, we can change the container image tag on the deployment, and a new replica set is created. Old one scales down as new one scales up gradually. So this basically means, let us say we are trying to have a deployment for inferencing, right? And it uses PyTorch. Okay, and then there is this particular thing about uh, certain things wherein this particular version, okay, is supposed to be rolled out or something should happen, in that case we will create three replicas, right, of the same uh, deployment, okay, for inferencing. We'll see as we go along, and when we do the lab, but the basic idea is we have to replicate the same container, okay, and then we would use one of them and then maybe improve upon something, and then basically try to what to say, roll out a specific replica, so on and so forth. So those things we can actually monitor and maintain using Kubernetes, right? Not going into the details very much, but these are certain things which will make us understand the benefits of Kubernetes, right? So, okay, so internal only virtual IP, cluster IP, default type pod to pod transfer within the cluster. Node port basically opens a static port on every node, simple but rarely used in production directly. So these are certain specific terminologies which, when people start using Kubernetes, will have to work with, right? So that is the reason I'm just briefly telling all of them, not going into the details, because this is a very, very exhaustive course in itself, but just to have a feel of what are the things people talk about in Kubernetes. We are just trying to have a very, very brief touch on to the fundamentals, right? Very briefly. So load balancer basically provisions a cloud load balancer that routes external traffic in. So client service thing with a stable virtual IP, and then pod any replica IP changes on restart. So this basically means that a service is the stable front door in front of pods whose IPs are continuously changing as they are rescheduled, because you are actually trying to uh, run a pod, okay, which has a specific IP, and that IP is used to access that pod. So if you actually close a pod, okay, or remove a pod from deployment, okay, then the next time the pod is generated, okay, the IP is going to change, right? So that is how it is basically to be understood, right? So GPU resource models in Kubernetes. There is this device plugin thing which people used to work with. It's a legacy thing. Like in resources, you had this limit set. So NVIDIA device plugin advertises GPU as countable resources, integer only, no fractional GPU without MIG or time slicing. So initially, since this concept of MIG was not there, okay, so this device plugin was treated as legacy. After MIG came, or time slicing came into the concept of GPUs. So multi-instant GPU, as we discussed, is available in Blackwell B200 or A100, also A200 also. So B200 actually supports 7 MIG slices, and then there is a time slicing thing also, so you can use these configuration plugins. But dynamic resource allocation in terms of support from Kubernetes for this particular thing has started from 1.32, I suppose, or 1.31 plus. Okay, so that here the resources which can be claimed is that GPU can be claimed, okay, and you can actually have a structured template with structured parameters, okay, which can claim MIG slices also, right? So the basic idea here is here dynamic resource allocation. When you talk about, you are talking of MIG slices, and then this means you can actually partially claim certain portion of the device, right, instead of having the whole GPU as in the legacy things. Okay, so now scheduler decision flow for GPU pods. See, pod requests one GPU. Which node advertises enough free GPU is what we have to check actually. So scheduler is going to do all that for us. It scores the nodes, rank by fit, and so on and so forth. Various ways of trying to understand how this ranking is arrived at. Then there is something called as binding. So scheduler writes node assignment to etcd. Okay, and then here basically the container starts. GPU device node is mounted in. Kubelet notices, pulls the image request device from the plugin, and then this particular scheduler basically writes and decides this node, okay, and links the pod's request, and the container will start in the pod, right? So something of this sort. So the basic idea here is container is going to start, your Docker container starts, my pod also requests, so I have to actually connect the pod along with the container. Okay, so if no node has a free GPU, for example, pod stays in pending. Okay, check with kube control describe pod. So this is very important. Okay, so there may be situations wherein your container will start, pod will always stay in pending because it will not have a free GPU. Okay, then what's to be done? Okay, so without auto scaling, pods will wait infinitely for capacity to free up. So that basically means your container is running. Or container basically starts basically GPU device mode is mounted in, but there is no binding which is happening so that it actually binds to the pod, and then pod is scheduled right on to the node where the GPU is actually there. So these are two different things which we should understand, and we should basically try to check, okay, with kube control. So one of the things in our case when we did, we simply did docker compose docker run, and we knew that there was a GPU available to us, so we simply did that. Now it is auto scaling thing which is being done. So this concept of pod will enter the docker. So docker will basically be inside a pod, and that pod has to be scheduled on a node with the GPU, right? So this is how it's going to pan out. So this is how the GPU pod manifest happens. We will see when we try to see our program, okay, when we run the lab today. So this is the API version, this is the pod, this is the metadata for it, specification, okay, how is that, which container, okay, so on and so forth, and then how is basically the pod manifest is actually written, right? So what does it mean to have this? Okay, we will see as we go along. And YAML manifest field by field. So let us try to understand this manifest here, which basically talks about runtime class name, okay, NVIDIA, then tolerations, okay, resource limits. These are certain things which basically we would be using in all of our YML manifests, and this basically means this manifest is going to tell the kubelet to hand off to the NVIDIA container runtime instead of plain OCI runtime. That basically means that if NVIDIA container runtime is not available, okay, we can go in with simple CPU runtime also. We will see, right, in one of our programs initially. And required means this taint sits on every GPU node Without it, the pod can't land there. So we will see what does it mean. Okay, so up till this particular taint is there, which is required. Okay, that means nvidia.com/gpu should exist. Okay, so then the actual GPU request, this is what the scheduler filter does, or scheduler basically tries to find out and then scores the node on this, right? So then pin to PyTorch matches this course baseline exactly, in the sense we're using all of this. And smoke test shouldn't restart forever on failure, never surfaces the error immediately. So that basically means the restart policy, okay, of what happens when something fails, right? So this is how basically it is. So taints repel pods. That basically means toleration allows pods to land on tainted nodes. Affinity attracts pod to specific nodes. So, for the time being, let us try to understand, okay, that what does taint mean here. Taints repel the pods, okay, and toleration allows pods to land on tainted nodes. That basically means if we taint the GPU node, okay, that basically means that every GPU workload must tolerate the taint explicitly. That means prevent the CPU workloads from accidentally consuming GPU quota. So that basically means, see here, we will ensure a very strict compliance to trying to only see that my GPU workload runs on the GPU. Otherwise, CPU workloads can consume GPU quota by some manner. Okay, which we will see what it means technically. But my CPU can simply sometimes, okay, uh, uh, accidentally consume GPU quota, right? It's not that we are intentionally doing it accidentally, right? Sometimes it might happen. So we must tolerate, okay, the GPU workload should actually wait, okay, and then based on the affinity we will try to see how that particular thing can be uh, resolved, okay. But for the time being, there are two words which you can keep in mind. There is called as nodes which are tainted, and then there is toleration efficiency, and taints are going to repel the pods. So if you say I taint and label a GPU node, okay, and I call it a tainted node, okay, so that basically means it's a strict thing of no scheduling, okay. And if the operator exists, then certain things will change, right? So we'll see what it means, okay. So does node have a matching taint? Pod is submitted. Any pod may schedule here. Pod must have matching toleration. Then affinity rule applies. So this is basically that only GPU requesting pods with the right toleration land on GPU nodes. Everything else is filtered out first. So the basic idea here is that we have to have a matching tag like thing, okay, and that is actually referred to as by taint. And then pod must also have the matching toleration, okay, and then pods are to be submitted to the nodes, and pods and nodes should have the matching taint, okay. So this is how it is. And then there are these namespaces, resource quotas, and the RBAC role, the cluster role, and then the limit range. So namespace is the logical partition of a cluster resource. Okay, so convention is one namespace per team or project. So namespace you understand, right? Resource quota limits total CPU, memory, GPU across all pods in a namespace, and it ensures fair share. So across all pods in a namespace, right? And namespace is basically a portion in the uh, cluster resource, right? And then we have this set default and maximum resource requests per pod prevents runaway single pods. So this is the limitation. And then controls who can create delete pods, okay? Then PVCs within a namespace, so on and so forth, that we will see, right? So just let us try to understand what does it mean, right? We're not utilizing this, but we are not going with the lab of this type. But for the time being, let's try to understand what does a one Kubernetes cluster mean. Multi-tenant cluster end to end is the condition here. So let us try to understand one Kubernetes cluster. Okay, so there is this namespace called as team alpha, and then there is this namespace called as team beta. Okay, so here there is this resource quota of 2 GPUs. Here there is resource quota of 2 GPUs, and then this for this particular team alpha, there is one pod which has 1 GPU. There is one pod which has got another GPU. Now in this case, there is 2 GPU resource allocation for this team. There is this one pod which is using 1 GPU, and then there is this quota headroom which tells 1 GPU is free. So team beta cannot exceed its 2 GPU quota even if teams alpha's nodes are idle. In case, okay, these become idle, okay, also uh, uh, team beta is not going to have uh, 2 GPU quota here. So this, the intention here of showing this is running, this is already allocated, so 2 GPUs are there, 2 pods are running, here one pod is there, quota is 1 GPU is free. You cannot have another GPU also free here. That's what it means, right? So quotas are per namespace, not cluster wide pooled by default. That's what is the intention here of this slide. Okay, so now let's go and try to understand how basically we'll start with uh, doing the programs in this particular thing. Okay, so let us go here, and if you go to week 3 as a Kubernetes lab, okay, this is having, I will explain in detail and then we'll execute the first one. So I'll just tell you like what are there in this. We have 5 labs here which we need to do. So today we will be completing the first lab, that is the inference service. Okay, and this basically has got 3 things. One is the Docker file, one is the tiny inference deployment.yml file, okay, and then app.py. So all of these programs will have YAML file, there is this Docker file, and then there is this app.py. Similarly here, in all of this we are working with YAML file, right? Now I have the readme also here, okay, of what each of these uh, folders have actually, and I have also tested it on my RTX 3050, which is 4 GB VRAM. Okay, so the basic idea is all these commands are actually running and verified working, right? So this is how the total, basically the file system basically for my lab week 3 is shown. Now, what is that this demo is going to teach is also written. It is containerizing a model server. The health endpoint returns 503 until the model finishes loading in the fast API handler. This is why Kubernetes readiness liveliness probes exist. Never route traffic to the pod that isn't actually running. Please understand this. We have to have a understanding that our Kubernetes should be ready. Okay, and for that we need to probe. So sometimes when you're trying to run, right, it might happen that it is not fully ready, and you will not be able to see, okay, the route of how basically to connect to a pod, and if it is not ready, what's going to happen. Okay, so that way we will have to understand the health checkup thing. Okay, so let us try to see another document which I'll first explain. Okay, and then we can actually, okay, so this is the lab guide which I have prepared. So first of all, what we will try to see is how Kubernetes readiness liveliness probes keep traffic away from a pod that isn't ready yet. So pod has to be made ready, right? We will see what are the various parameters which a pod is having to be considered as a full pod, right? And if that is not ready, we cannot actually tell a container to bind to that pod, right? And how GPU scheduling basically works, what are node labels, what are taints and tolerations, and the nvidia.com/GPU resource. Okay, so uh, we work with PyTorch. There is this read write once and read write many storages. Okay, not going into the details, but the difference we will be able to understand, and how resource quota and remit range is governing a shared multi-tenant cluster. Some of them is concept, but some of them we will run. What the NVIDIA GPU operator automates on a real GPU cluster, we will see that. Okay, uh, and then we will see. So before we start, uh, we should, at least I am assuming, that the Docker desktop is installed with WSL2 backend and Kubernetes enabled. I have written how do you have this setting. I will show you that also. And demos 1, 3 and 4 run on this cluster alone. Demo 2, the GPU pod needs a second GPU over cluster. Okay, so we'll see what does it mean. Okay, but we will have to verify the environment, Docker version, kube control configure current context, and kube control get nodes. Okay, so I have already started and executed some of the steps, but once you do all of this, you will be able to see step by step everything, right? So I will also try to show, because I have already done some execution which is basically running now. So I'll show you that, and afterwards we can see whether this is there or not. Okay, so from the inference service point of view, okay, we will come to this, but for the time being let us try to see the environment. So this is the Docker desktop. Okay, and this is the place wherein Kubernetes, okay, um, is actually now running, right? We are having one node. It's a kind cluster. We'll see what does it mean. But then deployment wise, we are having two pods running on that node. Okay, and then those pods are basically two tiny inference programs running. Okay, okay, and then if you go to the initial desktop settings, here there is this thing of enabling Kubernetes. So you'll have to actually enable this. Okay, so it starts a Kubernetes single or multi-node cluster. So if you have another GPU attached, which I will show you during some of the labs, we will have multi GPU cluster. That time the same thing, okay, can work with multi-node cluster, and we are now trying to work with a single node cluster, right? This is because it will be easy for you to experiment with before you go to a cluster. Okay, so this is a Docker desktop. This one node, it's running, so I started it maybe 2 hours back. Okay, and this is the cluster setting. So this which Kubernetes version I'm going to work with, I'm working with the latest Kubernetes version here. Okay, I can change the number of nodes basically. Okay, and then there is this option of kube ADM, which basically creates a single node cluster. Okay, and there are various ways of doing it. So I have used a kind type of approach. You can use a cube ADM type of approach. Okay, and then there are certain advanced things, okay, wherein we can see the cluster and so on and so forth. But if you have to again apply, okay, so I'm not going into that for the time being, but this is how basically Kubernetes has to be enabled. Okay, and then we will come here now, and so I showed you the document. Now here we started with, okay, directly running the script, which is that deploy inference services. So I will go to the script and I'll show you actually the way in which, okay, generally people who work with Kubernetes and people who work with containers basically try to develop their own script. Okay, so I am also trying to show you in that context instead of just typing everything, because it becomes easy for me to explain things, right? So let's go to this particular script, right? And this basically is like building and deploying inference service to a Docker desktop Kubernetes, and we will run it from a normal PowerShell. Okay, because we are working on Windows, I am trying to work with PowerShell. You can work with WSL prompt also. Okay, so one thing is we will have to set up WSL Docker, which is completed and which is basically verified that everything is working, right? So here uh, we are using Kubernetes context, Docker desktop. We are building an image tiny inference, which is local, and then we are trying to also see, okay, smoke testing the image locally on a CPU. At present we are trying to work with CPU. I have not yet uh, shown you the GPU thing, but for the time being, for this specific experiment, okay, we are trying to actually build an image, okay, and we are writing it for a local CPU host, and then we use Docker run name tiny this thing 8000 colon 8000 tiny inference local out. So this basically means this 8000 cross 8000 is something wherein you are trying to have your Windows environment and Docker's environment contacting each other, right? And then there is the sleep condition, which tells us about this program, wherein we are trying to see there is this mini cube which is running in the background, and sleep basically tells us that anywhere between this particular 2 seconds to 20 seconds is the time for we trying to decide, okay, the requirement for the CPU or the disk, okay, in WSL to be given to us, allocated to us, okay, for that specific pod. So this is how it is. And container did not become ready within 30 seconds. So see, the point is we have to check up for the health, right? That is what it means. And then we will tell deploying to Kubernetes, tiny inference deployment, roles, right, or pod. So kube control get the pod, the app is tiny inference, and then we say to test the cluster service run in another terminal, and we will have to see that the health of that particular thing. So what we did, we ran this, we told we are using Kubernetes, okay, from the Docker desktop context. Then we built that image tiny inference local. We will see what does it mean. We'll see that app, okay, and then we will try to load the build definition from the Docker file, okay, then all of Python, context, manifest, this and all, and then smoke testing the image locally. So I'm checking the health status is okay, the device is CPU, right? And then we are deploying to Kubernetes. Deployment is done. Deployment is done and successfully rolled out. So there are two pods here on which I have created two pods, and okay, no worries. So what I'll do is, yes. So here you see tiny inference. Okay, the age is 31 hours, and then the restart readiness gate 13 minutes 17 seconds. There are these are running. Okay, and the IP. If you see here, let me just take you to this thing. Okay, so don't worry about this comment, but yeah. So if you go here and see the thing, you'll see here the status okay, and then device CPU, right? And then this is the actual health. Now this is what actually we are seeing, right? So we have been able to run. So what is this app.py? Let us try to understand this first. Okay, so this is a minimal fast API inference service. So endpoints are, we can get the health, we can do, or after we receive it, receives a feature vector, returns a model output, and we can actually get certain Prometheus format metrics. Okay, so in a real system, the model would be loaded from an artifact store. Here we instantiate a tiny neural network model at startup, so the service has realistic load time characteristic. So the basic idea here is we are using Torch, we are using a fast API, and then we are trying to develop a model basically, and it's a tiny model, and it is basically in the container. Okay, and the model is basically a tiny MLP. Okay, it's a lightweight model, and basically the idea here is to show that a pod actually, okay, runs a small model actually. Okay, and it talks about if CUDA is available, checking if Torch is available, Torch CUDA is available, else we'll run it on CPU. So for the time being, it is just CPU which we are trying to run it on. And then the startup thing, so here this model thing, CUDA thing, basically, so there are certain things wherein the thing is ready or it's draining. Okay, and then the health thing used by Kubernetes readiness probe. So return 5 or 3 until model load is complete. Once ready, returns 200 and a small payload. So this is what actually we are seeing here, right? from the health point of view. And then, okay, and then, okay, yeah. So this program, if you go through when you're working, so this basically is a program which is a simple torch program with neural network model, just to have any Python program running inside this. So this tiny inference thing which we have put here, see here, API version is this, tiny inference, replicas are 2 because I am running it on 2 different instances, then 2 replicas, container port is 8000, health is this, okay, and then CPU I have requested, and then the memory, then there is this CPU limit, one CPU, and then here basically the port change. So this is the cluster. So here I have not yet given or requested for a GPU. That's why even though GPU is there, we are only working with CPU here. And then once we run all of that, okay, we can actually run this. And then so this is one thing. And now if you go to the Docker desktop, okay, and see the build here, okay, so for the inference service here, you can check the file name. It's a Docker file name. What are the sources here? What have you done it? The port mapping here, okay, and the info, if you see, local file transfers, the history, okay, and what all happened, right? The parallel execution. So what all not you want, right? What are the dependencies? What is the build result after each step? What happens? Okay, everything. So here you go here. What are the results? When, how much time it is idle? Okay, so build timing also. What does it each of these charts mean? Okay, so if you see the history, it will tell us how did it build, how much cache is used, when it was created. Okay, so I created one 8 hours before, another one I created 2 hours before. Okay, so how much duration it actually uh, is doing. So what is thus it mean? Okay, where on the cache steps, okay, how much is the cache steps, so on and so forth. Gradually you'll understand everything. Okay, but this is what basically is about trying to run, okay, our inferencing service. Okay, and then this is inferencing service which I ran one day ago, so 9 hours ago, so on and so forth. Okay, so the active builds, you can see everything. So this is the Kubernetes thing. There are 2 pods running on one node. So this is a basic idea. So I can just edit the cluster also. If I want, I can create 2 nodes and then run basically 2 pods on each node. Okay, so I can do that also if I have the facility of trying to increase the number of nodes. Okay, so so on and so forth. So this is what I feel as the first lab which we will do of trying to understand certain things. And let me just now try to again run the things. I will just quit again and then see, uh, and then I will show you actually again things so that it will become easy for you, okay, to do things. So let us try to run certain specific scripts here. So let me run the script. I told you the steps which it will encounter. See here, it will automatically try to do everything, build the image again and try to do this. It will again, okay, trying to see the image running on a CPU. It shows me everything, and then the tiny inference thing runs on 2 things, right? And again it will show the health, so it will show CPU running. And then, okay, you can actually open this on a different window, okay, and see the connections handling and so on and so forth if you need separately to check. And in the meantime, you can see the dashboard again and see what happens. So let us try to see this dashboard also now. Okay, see here. So now if you see the source again, logs again, the history again, just now, right? Inferencing surveys, build steps. So if you see here, just see here, this 1 minute ago it was created, right? So 3 out of 9 build steps, 1 inference surveys. Okay. So the ID changed. Okay. So 1.9 seconds, how much time it took. Okay, so on and so forth. So these are certain things which will help us manage a lot of things actually. Okay. See here, transferring 465 bytes took this many seconds, so on and so forth. So source one, the info thing, right? So if you see here, local file transfers 0.0 seconds, and so on and so forth. So it basically started, and then when did build complete. So these are certain things which we basically did as a basics of how basically the inferencing thing, just running on a specific pod and then trying to run a specific model app and then linking it up. So this is what I thought we will do today, and we'll continue the next session tomorrow. Thank you.